Okay, so I think it's time to start the last talk of today's session. The speaker is Tetsuji Miwa. The title is Method of Algebraic Analysis in the Study of Integrable Models. But before starting the talk, Professor Namikawa is the head of the department of the graduate school, actually. Will explain some words about his academic career.
数学教室の専攻長の浪川です。最終講義に先立ちまして、簡単に三輪先生のご経歴を紹介、させていただきます。まずは三輪哲司先生は昭和46年6月に東京大学理学部を卒業し、昭和48年3月東京大学大学院理学研究科修士課程を修了の後、京都大学数理解析研究所助手、それから、同助教授を経て平成5年1月に数理解析研究所の教授になられました。その後平成12年4月にここの理学研究科の数学教室に移られ教授になられました。それで今に至っておられます。この間三輪先生は長年にわたり数学の教育研究に努め、数理物理学における可積分系、特に可解格子模型、ソリットン方程式およびそれらに関連した表現論、組み合わせ論の研究に大きく貢献されました。これらの研究成果は高く評価され、三輪先生は1987年日本数学会秋季賞、それから1999年には朝日賞、それから2013年、これは今年ですけどもハイネマン賞数理物理学部門を受賞されました。いずれもそこにおられる神保先生と共同で受賞されておられます。また三輪先生は京都大学においても大学院理学研究科副研究科長、それから高等教育研究開発推進機構副機構長等を務められ、大学の管理運営等にも貢献されました。それでは三輪先生、よろしくお願いします。
When I was younger, I don't say I was young, but younger. It takes just several hours to prepare a talk, but these days it takes many times, and recently I start preparing when I arrive at the conference place, and I can only finish the preparation only after my talk or something like that. And for this talk, in fact, I couldn't even start, kind of. But I gave the same talk last week, and in 2 weeks I will give another same talk on Ising model, and this is the first kind of work with Jimbo-san and Sato sensei, so I am happy to talk about this. So my title is, well, algebraic analysis. And the title of this conference is Infinite Analysis. And so maybe let me first give a few words of what these are. So algebraic analysis, I think this is to study functions through equations. So then most of the mathematics falls into this category. But anyway, so I would rather say to study special functions by equations such as differential equations, difference equations, and so on. And infinite analysis, this is the origin of these special functions are from some system with infinite degrees of freedom. And usually in generic case, function which arises in the system of infinite degrees of freedom that does not satisfy, cannot be controlled by equations. But if the system has symmetries, possibly infinite dimensional symmetries, so infinite divided by infinite becomes some finite, and in that case we can describe or control the function by equations. So this is more or less what okay, so now let me give a specific example of Ising model. So you consider two-dimensional lattice like this, and we put degrees of freedom at ij's point, which takes value plus or minus 1. So when we say configuration, this means you put plus or minus to all vertex. So it is something like collection of plus and minus. Okay, and then we define a kind of energy of this with this is parameter, and you multiply the adjacent, horizontally adjacent. So this is called spin, plus or minus, and also vertical kind of interaction. And we want to compute so-called partition function. This is called partition function, which is sum over all the configurations, so sum over all sigma of exponential to minus this energy divided by some parameter. K is Boltzmann constant and T is temperature. And so, well, this is funny formula. Z is equal to summation over all configuration of this quantity. And this quantity is kind of relative probability of the occurrence of this particular configuration sigma. Okay, so if you divide this by the total sum, it is just the probability of occurrence of this. Now, a more general quantity is correlation function, which is expectation value of, say, for example, you pick up 2.00 and mn, and so this big M, large M and N is the size of the lattice, horizontal and vertical. So this sum actually is 2 to Mn summations. Okay, so the correlation function is just expectation value, so summation for sigma, but this time with multiplication of these product of 2 points. And something interesting, well, happens. So we want to compute such a quantity in the so-called thermodynamic limit. Namely, we consider the limit of the lattice size goes to infinity of this quantity. So we fix this small m and n and let the size of the lattice goes to infinity. And so this is a 2-point correlation function. So in general, you can consider n-point correlation function. And so the meaning of this energy here is, I don't know which is which. So I think if E1, E2 positive, if the energy is plus, plus, or minus, minus, namely it is in equal sign, this is plus, otherwise it is minus, and this means it tends to in the same sign. So same sign is kind of lower energy than opposite. It means it can occur more in probability sense. And so it measures if this is yes. So such a quantity we want to compute in the limit. And here is something called spontaneous magnetization. In fact, this kind of system is a model for the two-dimensional magnetism. And so, of course, the real world is that our magnet is three-dimensional, but here we are talking about the two-dimensional kind of magnet. And the strength of the magnetization is kind of defined in the following way. So instead of 2 points, you consider just 1 point. However, if you compute this quantity honestly, because there is a symmetry between plus and minus, so this is simply 0. So it's not interesting. But if you add such a thing, which is external magnetic field, then because of this, plus is preferred than negative, so minus. So this becomes non-zero. And once you compute this with non-zero h, and let h goes to 0, this can be 0 or can be non-zero. This quantity is called spontaneous magnetization. And in fact, the graph of this quantity, when you write t in this direction and this spontaneous magnetization in this way, so it behaves like this. And namely, so before taking the limit of thermodynamic limit, this is just a sum of some simple quantities, but in the limit it shows such an singular behavior, and in fact, so I don't write the result for the partition function, or it's but for this, this is the following is a famous Onsaga-Young result. This is given by simply by this formula below critical temperature, and 0 above critical temperature, where this SI is sine hyperbolic 2EI over KT, where this E1, E2 are the parameter coupling constant. Okay, so now I'm going to explain the famous, result by Wu, McCoy, Tracy, and Baruch. This was, I think, around 73 or something, and probably many of the audience not yet born, or so what is the result? So they consider scaling limit, which is you just consider this 2-point function, but in the scaling region, which means the temperature goes to critical from above or below the critical temperature. And at the same time, you let these integer m and n large, so that the product of large m and small t minus tc goes to some finite number, say x. Similarly, n goes to large quantity, so that the scaled quantity becomes finite. And in fact, in this scaling limit, the function depends on only this distance between these 2 points, and so you can define kind of scaling function, which is a function of one variable r, and you have two of them. Oops. And their result is the following. This function can be given explicitly by the following formula using some function u, which I explain shortly. And so, some formula, and here is exponential, and this is so maybe I miscopy or something, so you please don't trust, but anyway, the point is, so when I teach calculus, this r and this r is different or something like that. But the point is this function u, which describes this 2-point scaling function, satisfies following nonlinear differential equations. And this function is called Pain-Levé third function. So their result was around 73 to 76 or something, but this function was, or this differential equation or its equivalent was known in the beginning of the previous century. So when I was talked about this, I always said known in the beginning of this century, but now I have to say previous centuries. Well, anyway, so this is the result. And our work was to find some mathematical background of this kind of link between system of infinite degrees of freedom, which is in model, and some nonlinear differential equations. And so I want to okay. So the idea is just to bring so we sum up over two-dimensional lattice, but we split the summation into the one-dimensional slice and repeat in this way. This repetition is just a matrix product. So in fact, you can introduce some matrix. So you see, here, this is C2, two-dimensional, so one spin up or spin down, so this is a two-dimensional vector space, and you consider, so you see, taking summation is taking trace of each such two-dimensional space, and this is M. So this is a system which is acting on C2 M space. So one can define some huge matrix. Huge, I mean the size of matrix is, let's see, something is wrong. No. Yes. Something. Nino, yeah. Nino M Joe. Yes. So I can rely this audience. So you see. So this is very big. So I was told this by Sato Sensei, and this is big. This is very small. This is what we learned. So in fact, the problem is yes, and I don't skip the definition of V, but the property is the trace over this big space. If you take the power, nth power of matrix V and taking the trace, then you get this partition function. There is such matrix. And in fact, in order to so one problem is to compute the largest eigenvalue of this matrix. And it is enough and necessary in order to compute correlation functions. Because when you compute correlation function, you compute something like this. Here is some operator which represent the spin. Actually, for example, in this, suppose simplest case, sigma 0, 0, and sigma, which is which, m 0, then if you consider, so sigma z is this Pauli matrix, and sigma x is 1, 1, y is I minus I. Then if you put this 0 here and m here and some, well, maybe this is enough. So, and take trace and just normalize it. Then in the limit m and n goes big M and big N goes to infinity, it gives the two-point correlation function. And because of the Frobenius, in such a computation, the largest eigenvalue only matters. So you want to know about largest largest eigenvector, eigenvector, which is called vacuum vector. However, it is not necessary to know about the explicit formula of this vector in such a huge dimensional space. But so the problem can be reduced to this 2 to m, the huge big number, to rather small number, because, well, there is some so-called Jordan-Wigner transformation. This is to introduce some element in this algebra, huge algebra, which is, say, Pm and Qm. And they are fermion. Namely, these are such huge matrix, but their commutator, anti-commutator is just C number. So we can introduce such a thing, fermion, and you can consider the space of fermion, which is linear combination of these fermions. Okay, so this is dimension is what, to m, I suppose. And the good thing is V itself belongs to this huge space, C2 to M. However, this induces, the inner automorphism induces orthogonal transformation of this 2m dimensional space. Therefore, so you see, this is huge algebra, which is called, Clifford algebra, but the structure of V can be understood from its induced orthogonal transformation. So this is just the size essentially m square. So this is kind of tractable. And so actual diagonalization is just change the coordinate, change the basis from Pm, Qm to by Fourier transform. So you see this m is in the limit sits in integer. So in the Fourier transformation, you can change the basis, and you get some continuous variable. And then after that, so say, for example, theta. So instead of Pm, Qm, you can introduce kind of, well, I don't know, something like P tilde or Q tilde theta. And then the diagonalization. So we want to find the largest eigenvalue and other excited states. And the problem reduces to find to diagonalize this inner automorphism, not the big one itself. And you can diagonalize it by Fourier transform. Then the problem reduces to 2 by 2 matrix diagonalization. And you can do it explicitly. And now the result, so these are the famous work by Onsaga, Kaufman, and a few other people before McCoy, Tracy, and Baruch. Anyway, so yes, so I said I went to the thermodynamic limit where the size of the lattice becomes infinity, and Fourier transform to the continuum S1. But then we can further go to the continuum limit. Then this both becomes just R. So in this way, you can introduce some operator parameterized by U, which is the real number. And this still kind of ideally it belongs to this limit of this thing. So this is only ideally, but anyway, the point is these are creation and annihilation operators. Namely, 1/2 of them kill the vacuum, say U. Namely, if it acts on some eigenstate, it increases the eigenvalue of this matrix V. So since this is the lowest eigenvalue, so you cannot create new one. So it means it kills. So such an operator is called annihilation operator. And all other states can be obtained by acting these fermion operators on vacuum vector. So this is a general picture. So now the problem is to compute the limit of such a thing. And we need to introduce two operators. They are called, one is called disorder, and the other called order variables. Variables means, say, operators. And the order is just simply this sigma z. So this one, but we are interested in the scaling limit. And the other one is in the finite lattice, it is the product of from 1 to up to some, say, m of the sigma x. Okay? And in fact, if you consider in the region where temperature is less than critical temperature, this has one such disorder parameter has 0 expectation value, and as I explained already, this spin operator has non-zero expectation value. So we suppose now, and so you see, here I'm talking about these operators on the first line, but you can go to in this direction by putting developing it by inner automorphism of V by definition. So in general, you can introduce disorder variable with two arguments, and similarly order variable. And we consider that its scaling limit, not only thermodynamic limit, but also taking scaling, continuous scaling limit. So you have certain operator, mu and sigma. So we want to describe such a thing. And so what we want to do is Yes. So we want to compute, for example, 2-point function of this kind. And now we consider 1 plus 1 space-time quantum field theory, which means, so we have continuous variable x1 and also x2, which is the limit of small m and small n. But we just, so here the idea is called Wick rotation. Namely, you analytically continue this variable to x naught, and then this space of x0 and x1 becomes 1 plus 1 space-time Lorentz space. And we can, out of this Ising model, we can construct a field theory in this space-time. So, so first of all, everything you can construct in terms of this free fermion or creation and annihilation operator, because then you can compute anything you want if it is a simple expression in terms of this, because the structure, this vacuum expectation or action on vacuum of this operator is quite simple. Sorry. And the result is the following. Our operator is quadratic exponential to the quadratic form in fermion, and sigma is such. And here, for example, this Lx, this dot means because they are not commuting quantities, so we put annihilation operator to the right and creation operator to the left. So similar to we write differential operator in this way, not in that way. So this tells how to order non-commutative operator. Anyway, the point is this is quadratic in fermion. And I can just write simple formula. Okay, so depending on plus minus of u and u prime, it contains the creation part, creation annihilation part, and annihilation part. And you exponentiate, and that is the limit of this disorder operator. And order operator can be, you need one more linear in fermion operator, which is pardon? X, yes, good point. Times exponential minus I x minus u plus u prime plus x plus u inverse u prime inverse x plus minus is x0 plus minus x1, something like this. Okay, thank you. And well, 1/2 or anyway. So psi 0, this is just linear. Du, the same measure, and just only nothing here, just this. Okay, so these are the results. Now I want to derive, I want to say something about such a quantity, the 2 point. Well, so now I denote this as 2 vectors. I want to say something for this quantity or this quantity. And in fact, they are, well, so if you consider, so you see, this x0 and x1 is Lorentz, and this x1 and x2 is Euclidean. And the Euclidean function is nothing but, so r is the distance between x and y, then I don't know which is which, but one is these tau plus minus are nothing but these 2 point function. Okay. So the question is how to characterize such a thing. Okay. So this is a result of McCoy and others says these are governed by nonlinear differential equation. But where this equation comes from? It comes from linear equations. So we introduce another set of fermion to component, and this is so now I put this and then fermion. Okay, and so there's no reason to insist on the Lorentz space, but let's go back to the Euclidean space. Then, and let me use the variable, complex variable. So the quantities depends on both z and z bar. Now, this operator as a function of z, it satisfies the following Dirac equation. Namely, let's see. So let me call this as z plus and z bar d minus. Then if you differentiate, you flip. So if you hit by u to minus, then you flip this sign. So this is equal to minus, well, with some sign, minus plus. Okay, so plus minus after differentiation goes to minus plus. Or you can introduce 2 by 2 matrix operator, such a thing, and then any and so you see, if you consider any, say, w, which is the function of this, and in such a formula, psi plus minus this, well, I often abbreviate z. Z bar is cumbersome, so just say z, but it depends on both. And here is something. Then such a quantity, actually it is plus minus, satisfy d and w plus w minus equal to 0. So it satisfies just Dirac equation. And now I put here sigma and mu, namely I introduce, so we call such a function as wave function of quantum mechanics. And so let's define z with n point, which is plus fermion and mu almost everywhere except sigma at ith place. Okay, so this is so you can define plus minus in this way. Okay, so this is at least each wi. Whoops. So this is, yes, this is wi. So I means you insert sigma at ith point, and otherwise, so this function depends on parameters which tells you the position of the these order or disorder variables. Okay, so now the theorem which we proved almost 40 years ago is the following very simple result, namely, so consider the space of function parameterized by n point such that so function here satisfies the following properties. First, it solves Dirac equation. Second, if so you see in the two-dimensional Euclidean plane there is a to a n point, and if you go around any one of these points, your argument z, so this is a function in z bar, and if you go around any point, it goes to minus. So this is kind of double valued function. So this is when ai and going around. Okay, and we better fix the boundary behavior, namely, if z approaches one of the branch point, it is something like a square root inverse. And also condition at infinity, which is exponential damp with something, well, something like this for z goes to infinity. Okay, so let's consider, well, in fact, the statement is our wave function belongs to this space. Such a statement can be easily checked by this expressed formula of these operators in terms of fermion creation and annihilation operators. Okay, and in fact, the dimension, well, actually, this is the theorem. So dimension of this space is n-dimensional. And in fact, our n-point wave function gives the basis of this space. Basis. For example, if you consider a 1 point case, W plus of Z is just some constant times exponential to R, and here comes Z 1/2 and minus the same constant minus here, and this is Z bar 1/2. So in general it is more complicated and depends on the these branch point, but we know the basis of this finite dimensional space in terms of expectation value of product of field operators. Okay, so now we have more linear equation. So more, I mean they are solving Dirac equation, but not only that. So our 2x2 operator is, because of their constant coefficient, they commute with just differentiation with respect to Z or Z bar. So this is actually, well, so let's not write, but so these are commuting, but not only that. If you, so you consider two-dimensional motion group, and this is translation, and rotation is given by this, and it also commute. And what is the consequence of this symmetry of Dirac equation? So for example, if you apply one of the wave function, if you apply m of z, this still satisfies Dirac equation because of this. However, the singularity behavior which I, yes. So because I differentiate, so the singular nature, it becomes worse. However, the same thing happens if you consider differentiate by z or z bar. Therefore, if you subtract with certain coefficient, all the singularities at each branch point becomes get back to the original condition. So if you differentiate once, it becomes 1 degree, 1 power worse. But same thing happen here and there. So if you take certain linear combination, you can get it better. And further, if you subtract something like this, then you get to something better. Better means 0. So you can establish such a linear equation starting from this. And similar thing you can do if you differentiate with respect to branch point. Again, you get many unknown coefficient, which so you see these coefficient of the linear differential equation, they all depends on our branch point parameter a1 to an. So the conclusion is we have so-called holonomic system of linear differential equation, this, that, and the Dirac equation. So I mean here, I mean again, Wi differentiated by the branch point has similar expression with some other coefficient, and same for this. And the totality of these equations is kind of holonomic system of linear differential equations. But So in calculus, we tell such a thing. This is one very important formula. And if you have so many, linear equations, you cannot have these coefficients arbitrarily. There are many kind of consistency or compatibility condition arises here, and they give you some nonlinear differential equation for these quantities with respect to the differentiation with respect to branch point. And moreover, these coefficients, so you see what we are talking about is so what are they? So this is some vacuum to vacuum expectation value of psi of plus minus z, and here comes sigma ai or mu ai. And in fact, if you, so this is so-called operator product expansion. So if you consider this when z approaching to this branch point up to some constant, it start from the expansion start from mu and vice versa. So if you the product of this linear fermion and our operator, then the expansion start, operator product expansion start from sigma, vice versa. So namely, when you compute these coefficients, you want to compute the singularity, top singularity, the coefficient, and you can compute it kind of closed. So you start, everything can be computed in terms of product of sigma and mu. So, and in fact, this was what we wanted to compute. Therefore, so we can summarize that. Well, this must be, I think, carefully studied, but in principle, these quantities satisfy nonlinear differential equation with respect to these variables. So this is a very brief explanation of our things. Okay, so this is only maybe one example of algebraic method of algebraic analysis in the application to infinite analysis, the system with infinite degrees of freedom. And how many time are left over?
Not yet, a few minutes.
Few minutes. So I like Academy Award, or this is not an award, and in fact I was sentenced 2 more years in the prison. So it's not at all liberation, but so yes, and well, actually.
Sorry, 30 minutes.
30 minutes, I see. But so I prepared 3 pages. So this is 7 pages of this, and 3 pages of a kind of acknowledgement. And I think I cannot finish, but I can start at least. Well, so this happened because of this. Is this correct word? Poop. So maybe not. Yes? Poop or poopok. Poopok. Poop. Now you understand. Yes. The day before yesterday, Korea recalled me some funny story about me and Korea Reshethin and Dreamfeld. when we fly from Moscow to Paris, and actually the final destination was Lumini in Marseille. And first thing was Drinfeld, his suitcase, no, attache case, so-called, the small one, something like this, it was broken. So I gave him the suitcase band, and he put my suitcase band in this way, and he carried it on the plane. This was about one of the memory. But what about this? Well, yes, this means, well, yesterday so my English is very button, or more advanced word is neighbor, and my wife knew this. I didn't know that, but anyway, the story is about Oheso. And what is it? So I don't remember, but anyway, on the plane or airport, we talked about some common characteristic feature between Mongolian people and Japanese people, and I thought I explained that the boys or girls, Japanese, they have some blue kind of spot in the back. However, they of course they don't know such a thing, and it seemed they misunderstood completely, and they didn't believe. But since I say in serious face, so they wondered maybe. And in Lumini, there was Morita's family. Maybe you know Morita in algebra, and he brought his boy. And on the table of dinner or lunch, I don't know, Drinfeld pushed Collier to check if Japanese boy has poop in the back. So you see, these days our English conversation is such a very with misunderstanding. But so this was a kind of Madeleine for me. I'm talking about Proust. I never read through, but I immediately sleeps when I read Marcel Proust. But anyway, so this story that day before yesterday gave me all the memory of all these 30, 40 years. So well, I could have changed my talk to these 3 pages and just to say something like mathematics, still mathematics, but places and people. And I try to memorize all what I can recall in these 3 pages, but I'm afraid I cannot finish. But I maybe a little bit of these things. So it's a long time ago. So you see, my talk, the symposium of this symposium is infinite analysis. What? Past, present, and future. But my talk is only past, not even present. So Sato sensei, I think Jimbo-san verifies this statement, and at the end of every summer, he started saying that young guy like you feels sad at this time of the year or something. like this. He always, well, always means 2 or 3 times, but he talked such a statement to us. Well, for this, I have some. Well, yesterday I thought I have some different feeling about the end of the summer because, well, this is my Setsuko, my wife, about. So we are same. So since 12 years old, the beginning of the junior high school, yes, and we are in the same class, and so after the summer, the girls and especially her wear changed back to winter ones. So one day he showed up with blue, not white. And I felt, oh, this is new season or something like that. And I cannot properly say in English. But I think you understand something. But so she's very well. Anyways, so I have some different feeling about the end of summer. And so you see, I want to analytically continue from this statement, namely, so one of the problem of analytic continuation is you don't know where you go, but you must go there. So in 2000, I moved from RIMS to math department, and because I thought it's boring to stay in the same place for more than 25 years, it's just such a reason. But I didn't know what was the analytic continuation, and but the last 2 years I spent the analytic continuation is vice dean, and furthermore 2 more years kind of in the prison. So analytic continuation is very dangerous. But anyway, I start from the Crete. So Setsuko and Yasuko Akitsune, these are my children, and Professor and Mrs. Sato and Jimbo-san, we all traveled Crete. This was Soliton meeting, and I don't know if this was during the lectures or only in the lunchtime, but anyway, we put some blackboard on the terrace, and so we computed the tau function there, and KP tau function, and this was just kind of memory. And there was Professor and Mrs. Kraskar, and I still remember Mrs. Kraskar. She's very good at swimming. Well, for me, it is difficult to float on the water. I just, but Mrs. Kraskar is very gracefully floating and very good swimming. And another occasion, our family was staying in Kraskar's house, and this was, he invited me and Jimbo-san to giving a lecture, and our titles are about tau function. But he made some announcement. So I don't remember how he do this, but anyway, this can be read either tau or tau. So his announcement is tau or tau or something like that. And the two figure of person. I think he meant one of these are me and one of these are Jimbo-san. But for me, there are two kind of Chinese people bowing, something like that. But anyway, I record such a memory. So of course, this story is not based on the fact, but from the deformed memory. So you should not believe it. But still, and I remember the night before the lecture. So my wife and the children are sleeping in the bedroom of classical home, but I have to prepare the lecture for the tomorrow. And for at that time, as I said, I had no problem. After 2 hours or 3 hours, I can finish. But still, I remember even in this kind of old days, I was lazy not to prepare lectures beforehand, and so yes. Yes, and the next thing which I record is yes, this is also now this is with Sato Sensei, and this is about Whiteman's afternoon tea, and maybe Jimbo-san, you remember. So when we visited Princeton, 3 of us, we are invited. So you see this function, you continued to Euclidean region is called Whiteman function because he formulated this axiomatic way. So actually, these three people coming from Japan gave a concrete example of Whiteman functions. So well, I don't know if it was the reason or not, but he invited us to an afternoon tea at say I don't remember, but maybe 2 o'clock in the afternoon or something, and then Sato Sensei proposed us, let's have lunch, because 2 o'clock is, this must not be a lunch. So maybe only tea or something. So if we don't eat, we become hungry. So let's eat. And we went to restaurant and ate a kind of full lunch. And then we went to Whiteman's house. But they offered us kind of another lunch, and so I think I ate all because I was young, but Sato Sensei could not finish. So this was about Princeton. Well, but maybe for Sato Sensei, I must tell not such a kind of mistake, but his brave behavior at the New York airport. Namely, I don't remember why we stayed in some hotel near the airport, but anyway, 3 of us thought there is some van or taxi or something. So we thought this car must bring us to the hotel. This is a kind of shuttle bus or shuttle taxi of hotel. We decided. I don't know why, but so the driver started, and then he said, $20 each, or something like that. So Jimbo-san and I realized immediately, this is not the free shuttle, but maybe for just $5 ride, we must pay each $20 or $100. I don't know. But Sato Sensei was different. He immediately started fighting not like this, but you know, so go to jail or such a thing was, and finally the driver stops and we get out of the car. So sometimes, often he was very strong like this. Well, yes, and so I'm. Yes, this is about the taxi, and yes. And yes, one thing is maybe our first visiting foreign country, and this was so-called EST meeting in San Francisco. This is Earhart science training. So some guy called Earhart made big money by science training, and he wanted to be a physicist, and so he invited physicists and make a seminar in San Francisco, and Sato Sensei was invited. And we decided we also should be invited. So without invitation, we went there. And well, in fact, there are kind of another meeting in Stanford, and this meeting was in San Francisco. So at least we can attend the Stanford meeting. And yes, and how was, yes, after Sato's talk, they all agreed, please come. So Jimbo-san and I was admitted as a participant. So and then I think I remember in the evening after the session, so you see, we are three of us, and there are TTU and Barry McCoy and Sasha Polyakov. So you see, so we discussed not in 6, but so Wu, McCoy versus me, and Sato Sensei and Jimbo-san with Polyakov, if I'm correct. And what was it? So these two people do this, and because he was talking about the three-dimensional Ising model or something like that. What we did is two-dimensional Ising model, and he's talking about three-dimensional. So what was that? So these two people try to do this, and it's opposite. so for them, they did, you know, two-point function, and they start to understand the endpoint case. But they, according to Barry, one day they found our preprint solving the deformation equation, and so they asked me every detail of how this line goes to this line or something like that. And so our discussion separated into two groups, and well, I don't know, 1 hour or half, and these people are somewhat satisfied, and I'm afraid these people are not satisfied. Something like this. So maybe it's about time, or what?
Still have 10 minutes.
Maybe 10 minutes is okay. So yes, and yes, this is all about Barry McCoy-san and Park-san. This is famous. I wrote already somewhere, but probably not many of you do not know this story. So not this occasion, but later, I think only maybe again 3 of us visited Stony Brook, where Barry McCoy. And so we arrived at some airport, New York, I don't remember. So I thought Barry will meet us, but not. Instead, Jack Park came and bring us to the Stony Brook. And next day or 2 days, we met Barry, and he asked, "What are you doing?" And we explained now not continuum limit, but lattice correlation function and how it satisfies some nonlinear equation or something like that. We have no paper, but because we start computing such a thing, so we very naive people talked about this. Then from next day, Barry McCoy disappeared. And Parkson does not know where they went. And maybe next week there was a banquet in dinner at Barry's place, so we went there. Then Barry came to us, and I'm proud to say that we proved the lattice correlation function satisfy nonlinear partial differential equations. difference equation, yes. So he was kind of going back and forth with Stony Brook with Boston, where TTU was there, and even so, Jack Park was postdoc in Stony Brook, but for this. TTU, only TTU with Barry McCoy and Parkson separately. And since we talked about something similar, difference equation or something for the lattice correlation, well, actually our equation was not difference equation. Yes, differential equation. But they thought we are doing the same thing. So immediately Barry returned to Boston and write up their papers, and he was proud that anyway. So the final result of this story was kind of happy because all three groups, TTU and Barry McCoy and Jimbo-san and me and Parkson himself, derived some difference or differential equation. They are all different. So sometimes not collaborate, but just think independently is better than just do it all together. Okay. So yes, and so maybe I want to say something about Rodney Baxter. Because well, so the today's talk is only about Ising model without Baxter thing. But what we did later is the basis is the Rodney Baxter's work. So maybe I can tell you when we first met Rodney Baxter in Torino. So we thought we are meeting with Baxter. So we cannot go without any result. We must do some calculation. So we decided to do some calculation. So he invented the method of corner transfer matrix, and he computed such a one point function. So using model case, this was on Sagayan, and Baxter invented a systematic way of computing one-point function of such solvable lattice model. This was corner transfer matrix method. So we invented some new model and we computed the one-point function. So now we can meet Baxter. And we went to the Torino, and so when we went to the lecture room, he was giving the lecture. So after the lecture, we went to the Baxter, and we did such a calculation, and we computed one-point function. Then he said, yes, we have computed a series of models. So this was ABF models, a famous one. So he said, yes, we computed one-point function for the series of models. So we are shocked. We have only one new example, but he has already infinitely many cases. And but then I don't remember, but maybe he asked us, what is the power of Q? And we answered, it is Q to 6. And the next day he came to us, no, your case is not included in our list. So we are very happy for this. And yes, for example. Yes, and yes, and well, so yes. So, but maybe okay. So maybe I think we should mention some words about to Ludwig Faddeev, and so well. So when I first went to Moscow, Leningrad, this was me without Setsuko-san, but Jimbo-san with Yasuko-san. So the wife, Sato Sensei's wife, and Jimbo-san's wife, and my daughter, all Yasuko, same name. But anyway, so yes, so I think we did not meet Faddeev in Leningrad because he was in Paris or something like that. But but Jimbo-san says we met. So of course he's correct, but my memory is deformed in this way. So maybe, in my memory, I went to Sakurai, and there I met Faddeev, Ludwig. And he asked, after his lecture, he asked me, what are you doing now, or something like that. So maybe this was not the first time we met, but yeah, but so I said this, we are some calculating difference type soliton equation or something like that without much convincing what I'm saying. But then he said, you should study quantum spin chain. And I think we did not study quantum spin chain immediately, but after several years, we came to this problem. But I can tell you, maybe this is the last, about India, because India is my kind of, for me, and maybe for you, this is kind of another planet, but for me, this is very, well, so it's warm and a nice place. And so the first time I went there, there was some conference or workshop, and from Russia, Faddeev, Leon, Takhtajan, and Vladimir Korepin came. Is that correct? Yes. And I remember Leon was horse riding in one place. But for me, it was a trouble, because I ate something on the way to the Panchigani, where the workshop takes place. Eat from the, you should not do this in India, but I did. So as soon as I arrived in the conference place, for the first week, I go and back the lecture hall and bed. So I give some lecture on the Ising model and go back to the bed and stay there, or such a thing. But Anyway, this was the first time, and I went to some bus trip for excursion or something. And so you see, Panchigani means 5 hills or something like that. And so it's a high altitude. High, kind of high, but flat mountains. And we went somewhere, and then going down to, so I thought I recall the word Shangri-La or something. This is a very beautiful lake was there, and we going down there on foot. And I think Fadef was very fast going down, and Sutherland, yes, and I talked, yes, we are going down in age very fast, something like that. In fact, when going up, Fade was the last. So something, and so on the way back to the Bombay, this was the hardest trip for me because after the bus start, I kind of immediately wanted to go to toilet, but I cannot stop the bus, and it was going down, but I looked at down to the valley, and there was some bus was, bus was there, of course, by accident. Well, I'm not sure if this is a true story, but what I remember is I saw some bus accident in the bottom of the valley, and our bus is going like this, and so it was really tough for me. But after such a experience, I liked India very much. And as some of you knows, I especially liked their clothes. Man kurta pajama, and women Punjabi suits, and I bought for myself and for Setsuko a lot of such a thing, and until Om Shinrikyo appeared, I wear this. I think, in my opinion, the kurta and pajama is the best suits for hot and humid weather in Kyoto, but because of Om Shinrikyo, you better not to wear. Okay, so I didn't tell a story about people here, but I think I stop here. Thank you very much.
Well, thank you very much for very nice stories. Are there questions? Is everybody satisfied? So there is 花束贈呈の方をお願いいたします。
どうも。はい、久しぶりです。どうしたんですって、どうもよかったです。ありがとうございます。どうもありがとうございました。